Hi, everyone. I'm Chris Humans. I'm a faculty member at Caltech, and among other things, I teach the Intro to Theory course, which this lecture is part of. And I've done that every year for many, many years since I've been here. And I really enjoy the material. It's actually this lecture, which is about NP completeness of 3-SAT, is one of those things that sort of got me hooked on theoretical computer science in the first place many years ago. So it's really fun to be able to give this lecture. My research is in complexity theory, having to do with the study of randomness in computation, which is sort of a related question to the P versus NP question, or analogous to that. I also work on algebraic algorithms and algebraic complexity. All right, so let me share. So I'm going to do this with slides. Share now. Okay. Okay. So NP completeness, the Cook Levin theorem. So let me start. Let me start by actually being able to advance the slides. There we go. All right. So let me start with a puzzle, just to sort of introduce 3-SAT. And actually, this is a really good way to think about 3-SAT when you're doing reductions from 3-SAT, which is part of what you'll probably have to do with this material later on in the course. So this is a little bit of a contrived puzzle, so just bear with me for a minute to while I describe it. So the challenge is the following. So it's a question about whether you can find an efficient algorithm to solve a problem, whether you can find a polynomial time algorithm to solve a problem. And the problem is as follows. You get a bunch of triples of symbols, which in the slides I've just indicated using characters, the symbols are alphabet characters. They're either uppercase or lowercase letters. There's 2 kinds of each type of symbol. So you get a bunch of triples of these, a long list, probably longer than these 4 that are indicated here. And the challenge for your algorithm is to look at such a list as its input and to determine if it's possible to select at least one symbol from each triple without selecting an upper and lower case of the same symbol. So the red characters on the slide is an example of a way that this sequence of triples is we would say a positive instance. There is a way to select one character from each triples, which is indicated in the red here. But there could also be sequences of triples where it's not possible. For example, the pair of triples, which is all. The first one is 3 capital A's, the second one is 3 lowercase a's. There's no way to do this, right? Because you're forced to choose both an uppercase and a lowercase a. Okay, so the challenge is, given a sequence of triples like that, find an algorithm to identify which type this is. Either it's possible to circle one symbol in each triple without uppercase and lowercase, or it's not. And that's a sort of a combinatorial type puzzle, and it's one that you could imagine kind of trying to devise an algorithm for. I mean, many of you might start to think about something where you kind of do a branch and bound, where you maybe choose one thing in the first triple, and then you go down the line and keep choosing the first one that's available to you until you see that one's not available, and so you have to backtrack and try something different. And if you play around with this a little bit, you'll find that there's lots of different approaches you can imagine that all seem to take exponential time. So the challenge is, can you find something that takes polynomial time for this? But anyway, that's a problem that is good to keep in mind, a puzzle that's good to keep in mind. And the reason that it's relevant for this lecture is that it's a disguised version of the language 3-SAT, which is the problem that we're going to show as NP complete. So 3-SAT is the language consisting of those Boolean formulas that are in conjunctive normal form with 3 literals per clause for which there exists a satisfying truth assignment. And just to unpack some of that, conjunctive normal form just means that the formula, which an example of which is written down here, is the and of ors. Okay, so these are ands that connect things, and then there are ors inside each of the parenthesized expressions. And each of those parenthesized expressions is called a clause, and each of the variables or its negation is called a literal, and there are 3 of them in each clause. Okay, so and given such a formula, the three-set language consists of those formulas for which there is a truth assignment to the variables that causes this whole expression to evaluate to true, satisfying truth assignment. Okay, now that I'm claiming that that is the same thing as the sort of puzzle problem that we identified on the previous slide. That is to say, if you have an instance of the puzzle problem, which is the sequence of triples like we were looking at before, then you can translate that into this three-set form by taking like the letter A becomes the variable x1, uppercase occurrences appear positively, and a lowercase occurrence occurs as a negation of x1. And then B gets translated to x2, and since there's a lowercase b, it becomes negated x2, and so on. And I think that you can see that if there was a way to choose one symbol from each triple among this sequence of triples, well, if you make those corresponding literals in the clauses true, and then set anything else that's not set any way that you like, what you'll end up with is a legitimate, satisfying truth assignment, because you'll have one true, at least one true in each clause, which is enough to make this whole expression true because they're connected by ands. And because you never circled an uppercase and a lowercase, or never selected an uppercase and a lowercase of the same variable, it's a legitimate truth assignment. You're never going to try to set x1 to be true and not x1 to be true at the same time. Okay, and it works both ways. If you have a truth assignment to these, oops, do that. If you have a truth assignment to these, to this 3CNF formula, then you can just select, you know that if it's a satisfying truth assignment, it has to have at least one true in each clause. You just pick one of those true literals and select that for your selection among the triples, and you will never choose both an uppercase and a lowercase of the same character because it's a legitimate Boolean truth assignment. Because it's a satisfying assignment, there'll be at least one to choose from every triple. Okay, so there's a correspondence between these two. And I mention this just because having both of those interpretations in your mind is sometimes useful when you're doing reductions from three-set. And also because it sort of explains why it plays such an important role in the theory of NP completeness, which is what I want to say next. Let's see here. So the Cook Levin theorem, the topic of today's lecture, is the theorem that states that three-set is NP complete. And I wrote that that's the gateway to proving lots of natural important problems are NP complete. And that's because three-set has this sort of puzzle flavor to it, which I tried to bring out, combinatorial puzzle feeling to it, or at least combinatorial feeling to it, that doesn't make explicit reference to computation in any way. But because it has this sort of combinatorial puzzle feel to it, it can be easily reduced to lots of other problems that have to do with combinatorial type puzzles, like other problems that you might have seen or will see, depending on how the course is organized, like vertex cover, Hamilton path, clique, other graph problems, and thousands of other problems. But they all tend to have this sort of combinatorial feel to it, and because three-set is NP complete, that gives a starting point for lots of reductions. Okay, so that's the theorem we're going to try to prove today, or in this lecture, I should say. And I need to just remind you of a couple things which are probably have already been covered, but just so NP is the set of languages that are decided by polynomial time non-deterministic Turing machines. You know that. An alternate definition of NP, which you probably have also seen, which is important for this reduction, is this theorem that a language is an NP if and only if it's expressible in the following form. So the language is expressible as those strings x, for which there exists a y, another string, whose length is at most polynomial in the length of x, such that the pair xy is in a language R, where R is something you could decide in polynomial time. Okay, so the language can be expressed, a language that's in NP is expressible as those strings x, for which there exists a y, such that xy is in R, where that's something you can decide in polynomial time. And that's a nice thing because it doesn't make reference to non-determinism. It just talks about polynomial time computation, which is easier to think about. Okay, and then if you actually wrote down a Turing machine that decided that language R, you might call it M sub R, That's sometimes referred to as a verifier because it does this checking to see if XY is a member of R. And there's a couple of other bits of terminology that are associated with this. The string Y we sometimes call a witness or certificate because the existence of such a Y is a way of proving to yourself that X is a member of the language. If you have such a Y such that XY is in R, then you know that X is in the language. And if not, X is not in the language. And this feature that you can determine whether X is in the language or not by the existence of a witness that can be checked efficiently is sometimes called the property of being efficiently verifiable. Okay, and so this is just another, this is the theorem we're not proving now, but it's another definition, if you will, of NP. It's equivalent to the standard definition in terms of non-deterministic Turing machines, or you might have seen this one first. That's going to play a key role in the reduction. Okay, so the reduction is going to come in two parts. So first we're going to show that a related problem called circuit sat is NP complete. And circuit sat is just the same kind of thing as 3-sat. It's just that the instance is no longer a 3CNF formula. It's not something in that special form. It's just a arbitrary Boolean circuit. And I'll remind you what that is in just a minute. And the question is whether that, so the language consists of those Boolean circuits for which there exists a satisfying truth assignment. A Boolean truth assignment to the variables that makes the circuit output 1 or true. So that's the first part of the reduction. And then the second part is we're going to show the 3-sat is NP complete and we'll reduce from circuit sat. Okay, so let's start with the first half. We're going to show that circuit sat is NP complete. I promised you I will remind you or tell you what a circuit is, just so that we know what we're working with. So a Boolean circuit, C officially is it's a directed acyclic graph. In the picture I've indicated the nodes. Each node is labeled with an and, an or not, or with one of the variables. Okay, and or not, or one of the variables. And here's a little picture of one over here. I guess the important thing to notice is that the fan out can be more than one. So like, for example, this AND gate here, maybe I should have drawn a circle around it as the node, has its output going out to 2 different places. And in general, that may be true for any of the nodes of this circuit. So for example, the variable x2 may have its output going off to different places in the circuit, not pictured here, but that's possible. Okay, and I think you can probably see that if you choose a truth assignment, whoops, I don't know why I did that, sorry. If you choose a truth assignment to each of these variables x1 through xn, then there's a natural way that that truth assignment propagates up through the circuit. So x1 and x2 combine with an and to put whatever truth assignment belongs at that node there, and the other truth assignments propagate up, and then some truth value, true or false, pops out the top of the circuit. So in this way, a circuit C naturally computes a function from n bits to 1 bit in the way that we just described. And when we talk about the circuit, we're often going to sort of deliberately confuse the circuit, which is the graph with the labels on the nodes and so on, with the function that it computes. So we'll identify those two things. And the size of the circuit is just the number of nodes. Okay, so that's Boolean circuits. And then the one fact that we need about Boolean circuits, just to observe, is that any function that you can think of from n bits to 1 bit can be computed by a circuit of a certain size. The size is not so important for this argument, but in fact the size can be, let's say, n times 2 to the n for an n-bit function. I'll try to convince you of that here, and then that's just going to be needed at one later point in the proof. So one way to do it, there's many ways to do that, would be to say that you identify each of the x's, like, so this is x is now a vector of n variables. So each of the n-bit strings for which the function evaluates to 1, and you can construct an and of n literals associated with that x that evaluates to 1 on exactly that point and 0 everywhere else. Okay, so like if the x that you were thinking of was 1 0 1 1 1 1 1, then that and would be the and of x1, not x2, x3, x4, x5, etc., and so on. Okay, so you can construct an and of n literals for each x that evaluates to 1 on exactly that point and no others. And then you can just take the big OR of as many of those as you need to take care of all of the points at which the function evaluates to 1. Okay, and if you put that all together, the circuit you end up with has size at most n to the times 2 to the n. In fact, you can do better than that. You can do 2 to the n over n, something like that, but that's not important for this lecture or even this course, probably. Okay, so that's Boolean circuits.